starting partway through on a Chem 129 problem, we're thinking about a lab thing where we're trying to figure out what's happening with calcium carbonate dissolving. And calcium carbonate is an insoluble salt. We can write down this kind of calcium carbonate. We could say it breaks into calcium ions and carbonate ions. The KSP for this is pretty small. It doesn't happen very much. I don't have an equation sheet handy, but if I grab one real quick, calcium carbonate has a KSP of 3.3 times 10 to the minus 9. Doesn't dissolve much. And so we say, well, what ways can we affect the solubility of calcium carbonate? And we say, okay, well, we could do common ion effect. That would make it less soluble. Or we could try to do a side reaction. I'm going to put more stuff. Don't take a picture yet. Or you could take a picture and then another one later. Or we could try to do a side reaction and make it more soluble. So I've got two different kind of side reactions we can consider. And that is what happens when we add a strong acid. Well, if we add a strong acid, this is definitely going to react, right? Because we've got H3O plus with carbonate acting as a weak base. So that strong acid, strong base reaction will happen, and that will form HCO3 minus. And that's fine. That's one way to do it. We could also add a weak acid and set up the situation where we've got a competing equilibrium of how well does acetate give away its proton versus how well does hydrogen carbonate give away its proton. And so we've essentially got like you've got this Ka versus Ka situation. And the question might be, well, why would we bother doing this more complicated system when we can dissolve it with strong acid? And that's where the context of the lab becomes important. And that list of pKa's that you have. This is for a particular lab section question, but all of you are doing this lab. You just have different setups for the same idea. Like I do it very different in my class, but like my problem setup when I teach lab is really different from the one that you have. All the ideas are the same though. Right, so we look at this and say, okay, well, why would we do this complicated thing with competing equilibria? And that's because we're not just trying to do carbonate. We've got 4 different things that we're considering. Right? We've got carbonate. We've got oxalate. We've got, is it hydrogen phosphate?
Yeah.
We've got hydrogen phosphate.
BO2.
And, yeah, that one's pretty weird, though. That one, is it BO2? Was it?
BO2 minus.
Just like that? Okay, so I got it right. Now, borate's a weird one. We'll get into that later. But essentially, it goes through some weird side reactions when you put it in water.
Is this last week's lab or this week's?
Last week's lab. This week's lab with the lithium lab, you do a bunch of competitive solubility problems. So we look at this and we say, okay, I don't want to just check if calcium carbonate is soluble. I want to check if, and we put calcium with all of these. So we form calcium carbonate, we form calcium oxalate, and we form calcium hydrogen phosphate. We don't add base to make this calcium phosphate, do we? We just do calcium hydrogen phosphate?
Yeah.
Okay. And then, you know, I'm going to put it in a different color because the calcium borate doesn't really form.
Yeah.
Right? Because this actually goes through a side reaction. Right? Borate in water does some weird things, so that one doesn't actually form. So this is where the difference between a strong acid and a weak acid becomes more useful. A strong acid would dissolve all 3 of these. All 3 of them would dissolve. Because these have different KSPs, it might take different amounts of strong acid, but strong acid will dissolve all of them because strong acid will protonate the carbonate, the oxalate, and the hydrogen phosphate. Guaranteed, because it's a strong acid. With the weak acid, it depends on this difference of Ka's. Is acetic acid stronger than the hydrogen carbonate? Is acetic acid stronger than what would form is, so we got to consider HCO3 minus, Is acetic acid stronger than the hydrogen carbonate? Is acetic acid stronger than the hydrogen oxalate? Is acetic acid stronger than the dihydrogen, di for two hydrogens, the dihydrogen phosphate? And if acetic acid is stronger, gives away its protons better, then the side reaction will occur. If acetic acid is weaker, gives away its protons less well, the side reaction will not occur in any significant way. So, shorthand is we find the smaller Ka. So what's the Ka for acetic acid? Right, so now we can just do this kind of, you've got the list of Kas handy?
I have
Okay, yeah. What are the Kas for these different things?
But those are
Um,
PKs, so.
Oh, we can do pKas, that's fine.
Okay. So.
And we gotta flip our thinking a little bit because it's negative log, but
I have the K.
Can we just use Ka for a second?
let's do Kas.
Thanks.
What are the Kas?
For the carbonate one, it's 4.7 times 10 to the negative 11.
Is that for hydrogen carbonate or carbonate?
Yeah, hydrogen carbonate.
Okay.
For hydrogen oxalate, it's 5.37 times 10 to the negative 2. And then hydrogen phosphate is 6.2 times 10 to the negative 8.
What was the Ka for acetic acid?
5.
And for acetic acid,
1.8 times 10 to the negative 5.
this one is supposed to be negative 5. That's why I was making a weird face.
Oh, is it?
Yeah, you got this one, 5.3 times 10 to the minus 2, is for H2C2O4. That's for the oxalic acid, not for the second proton.
Okay.
And that's why I was also making a face about that one, but that's just because I think my memory is bad. Where is carbonic acid on here? Oh, there it is. That one's fine. Okay. Yeah, it was just that second one. Now what we want to say is, okay, so, and again, like, here's the funny part about this problem, to me. And same thing that's funny about so many things.
Sorry, so on the equation sheet, when it has 2.
First one's for the first proton, second one's for the second proton.
Okay. Oh, that's what I think that's what my thing was. Because I didn't know which one of the 1 to use because I wasn't, I didn't know. Okay.
Yeah, so second one for the second proton.
So I used that. but
One of the
that's
things that comes up often in
Oh,
Chem 129 that's really funny might be the wrong word, is if I just tell you the math thing to do, it sounds super easy. But all the conceptualization to get to that math thing is really hard, right? So the answer is, so like the math thing that we have to do is just say, which ones are bigger than this? Which,
Oh wait, sorry.
It's
Just oxalic acid.
right, just the hydrogen oxalate has a Ka that's bigger. That one won't dissolve. Because acetic acid does not give protons well enough to protonate it. Which means that one, the side reaction won't occur. And if no side reaction occurs, no increase in solubility. Right, mathematically, that's really easy. I'm just saying, tell me which one is a bigger number. But the conceptualization of why that's useful and why that's happening, there's a lot of thinking that goes into it. We have to think about the slate solubility. We have to think about the competition between the equilibria. We have to think about what's available to actually react to make those side reactions occur. And here, another hint, let me give you, you should get better at picking up on the sociological cues for chemistry as well. I know that's not how chemistry works when you're doing like research and you have no idea what's going on, but in a classroom setting, you can always pick up on, what was the name of this test that we're doing?
The oxalate test.
It was the oxalate test. Guess which one should be different in the oxalate test? Oxalate. Right, so we already had some hint of like, well, what kind of things should I be looking for? Which things should look different from the others? And it turns out oxalate is the only one that's got a bigger Ka.
Can you, could you explain, I don't mean in words, but could you explain one more time, relationship-wise, why having a bigger Ka will mean it won't dissolve in acetic acid?
So what we're looking for is, will a side, so when we look at our solid, we're looking for, can we make a side reaction happen with the anion? And we can make the side reaction happen with a strong acid for sure. And the question was, can we make the side reaction happen with a weak acid? And the only way we can make the side reaction happen with the weak acid is if we use a weak acid that is stronger than the conjugate acid of the solid's anion. So we have to have a weak acid that can give away protons better than the conjugate acid of the solid's anion. So, here's the carbonate. Is my acetic acid going to push H plus onto carbonate? Well, it just matters as to which one donates protons better. And when I look at this, when I look at these two, acetic acid is the stronger acid. It's going to give away protons better than this one. So that means when this equilibrium happens, acetic acid will donate protons, carbonate will go through the side reaction. It will be removed from solution, which means the solid has to respond to reestablish equilibrium.
So a larger Ka is that substance's willingness to donate its protons?
Yes. Right, so a larger Ka means the material is giving away protons better. Here, now if we switched it to looking at oxalate, we end up with this issue where when we form this Hc2O4 minus, it gives away its protons better than the acetic acid. So that reaction is going to push backwards more, because anytime we form this, it just gives the proton back to the acetate. So in this situation, the oxalic acid with the acetic acid, the side reaction doesn't occur because any hydrogen oxalate you form, well, we'll get into the details in a moment. In the simple version of it, that any hydrogen oxalate you form just gives its proton back to the acetate, and the reaction just ends up being back in the reactant side still. So no side reaction occurs.
And that's why we're not able to dissolve the calcium
Oxalate. Yeah.
Because
Now, the reason I got a little hemi-high there where I was like, am I lying to all of you right now, is technically when you look at these two, hydrogen oxalate, so that's the answer that the lab is looking for. That's the underlying principle. The place where my language got a little bit imprecise was the point where I said the backwards reaction completely happens or doesn't completely happen. We would actually, we're not going to do this till later in the quarter, we can actually calculate the overall constant for how much this reaction would go forwards, backwards, from calculating an overall equilibrium constant for the weak acid with a weak base. We're not going to do weak acid, weak base reactions until after we finish buffers. But on a conceptual scale, we can just say, look, it's gonna happen or not happen. That was a lot. Just say it's the smaller numbers, bigger numbers.
Yeah, that makes sense. My lab instructor was telling me that we do have to write out the 3-step equation and then kind of apply the KSPs together to get overall.
He wants you to calculate the K overalls.
Yeah.
Okay. We haven't done that yet. Technically, you could argue that you did some of that in Chem 128 because you did Hess's law and you did equilibrium constants that get put together. I don't really like to depend on people remembering Chem 128 too much this quarter, but technically it's you write out the 3 steps, you multiply the numbers together. It's pretty straightforward. So let's do that for one of them. Right, so let's do that for one of them and see what happens, and then we'll get back to doing other things and talking about quizzes if you want to. I'm sure it's typos. I'm sure it's some little things. So I'm going to erase this thinking on bottom. We're going to talk about the 3 equilibrium steps that are happening, and I hope I'm not getting them different from how your lab instructor wants them done, because we all do things that are similar, slightly different. So we've got that. Then we've got right. So we've got a KSP for how well this dissolves. Then we have a Ka for how well that gives away protons.
But then wouldn't it be 1 over Ka?
We're getting there. For the next thing? Right. So then we have one more thing to look at, which is the CO3 2 minus plus H3O plus goes to HCO3 minus. This is not a Kb. Remember? Kb would be carbonate with water. This is carbonate with an H3O plus, and that H3O plus is technically coming from here, right? It's the acetic acid donating, but we're looking at it in 2 steps. So this is not a Kb. What does it look like, though? If I write it flipped over,
It's like a precipitation.
it kind of looks like a precipitation because there's 2 things being put together. I didn't do my states of matter, so you can all be mad at me. But this is an ion in solution. So it's a combination reaction. If we wrote it the other way, this would be the Ka. You notice I've gotten lazy. I'm ignoring my waters. There's H2O just kind of implied in these. We get like that after we do too many of these. There's H2O implied in all of these. So you can't technically balance this unless you have the H2O because where the extra hydrogens come from and stuff like that. So I'm just trying to be quick though. So I say this is the Ka for it. This is actually just the complete flip of that, right? So while this is not Kb, this is 1 over Ka. And now I'm going to do some really silly labeling on these because you notice I get really confused. I don't know if y'all notice, I get confused pretty easily. But I get really confused when I've got multiple reactions with multiple Kas and Kbs in the same situation. So I put lots of labels. So I call this Ka comma acetic to make sure I'm talking about the Ka of acetic acid. And this is 1 over Ka, but it's not any Ka. This is 1 over the Ka of carbonate. So I just call it Ka carb. So that way I don't lose track of my Kas, because I will. When I was first teaching this class, I tried to call them all. Oh, we'll call this Ka AA for Ka of the acid acting like an acid, the Ka of AB. It just was a mess. I got to the point where I was like, I'm just putting the name of what it is. So it's the Ka of acetic acid divided by the 1 over the Ka of carbonic acid. And now I just multiply these 3 things together. KSP times Ka acetic divided by Ka carbonate. And so the reason I just focused, and your lab instructor wants you to calculate this just has a number associated with it now. You just say, is that number bigger than 1 or less than 1? Does the reaction go towards products or reactants? I was really just focusing on, well, what's this ratio? Is this ratio big or small? Because one's going to be bigger than the other. And that's the part that I was focusing on. Does that make sense?
Yes.
Cool. Okay.
I have a question.
About this or something else?
Something else.
Okay. Are we? Let me make sure. Are we ready to move on? Because I've also got a couple other problems that we want to work on.
So I add a problem to that list.
Yeah, and you can also add quiz questions to this list if you'd like.
Can I add number 14 to 2.2?
Okay.
So the Ka values for all 3 of these steps you can find on the equation
Yep.
sheet?
Yep. Now, You just have to be careful. Make sure that you're getting the Ka for the second proton of carbonic acid, not the first proton. So that's going to be the second number in the entry. This quarter, man. So the one of my problems with this quarter is there's like 5. Maybe I can design it differently. In any case, I'm thinking about course design. There's essentially like 5 important things that we have to do in order for the labs to make sense. But the 5 important things are like from different parts of the quarter. And it's like, can I just do all 5 of those the first day so the labs make sense on the first day? And it's like, not really, but maybe I could. I don't know. I feel like the review is more important. In any case, let's go ahead and do some of these problems. I'm going to erase what's on the board here.
I think you might have erased it, but could you just do the quiz question number 2?
Yeah.
That was written up there. It's
Can I just ask Joe, just like a
Yeah, now I'm ready for questions now that I'm done with this.
It's about 2.1. It's asking about forming any solid of like a compound. So it's where we have to use Q and K and then compare it. So in this case, I went through the whole process and I figured out that Q is greater than K. So for that reason, the right answer is yes, a solid will form. Can you like think or explain why, like if Q is greater than K, solid will form?
Yeah. So, and I will say, there's something else important that I would say. It's not just any K, specifically KSP is less than your Q.
Yeah.
So the thing that becomes important is when K is less than Q, that means we go towards reactants.
Oh, I thought we were going to the right. That's going.
No, because remember,
Okay,
this
so
is like.
Okay, yeah, that makes sense. Always write it at Q and then K and then whatever the little thing is.
Well,
going
let me show you the other way you can think about it. Right, now it's a ratio of products to reactants, and it's the equilibrium values versus like your initial values or your start values. I like start better, but let's go with that. Right, so we're looking at our starting values versus our equilibrium values. And so the thing that I focus on, I just focus on, because ratios are always hard for me, so I always just focus on the numerators. I know it's not technically the only thing you could do, but I just think about, okay, if my equilibrium, if I've got my KSP less than my Q, that means my starting value has more products than I should have. How do I get rid of products?
We are going to the left.
Shift towards reactants.
Forming more solid.
Yep.
Yeah.
That's it.
Yeah, I think it was just the way I wrote it as.
Oh,
Q.
you were trying to do the greater than less than trick?
Yeah.
You have to have K first for that to work.
I wrote Q is greater than K instead of K is less than Q.
Yeah.
So then I did the arrow.
Yeah. So to do that little shortcut trick I showed you, K has to be first.
Yeah.
Okay.
Can you also do number 4 on the quiz?
Yeah. Yeah. Okay, now let's see how many of these we can get through. We'll do quiz number 2 and number 4. This is quiz 1, yeah? Okay. Where should we start? Quiz 1.2 or 2.2?
Say that again?
Where should I start? Let's just go down the list.
Can you do the quiz question?
Let's do the quiz questions first. Okay, so what is number 2?
Find the equilibrium concentrations of the cations and anions in solution when you dissolve as much possible strontium iodate solid in water. Use the KSP 1.14 times 10 to the negative 7.
Okay. Same numbers?
Yeah.
Cool. Okay.
Amazingly.
So
I got part A right, so I could kind of explain, but part B.
Let's see. So we're looking at. Well, now I'm like, gosh, I hope I don't have a typo in the code because like I thought you would
I
get.
had different values.
You had different values.
I had
Okay.
a whole different compound. Like I had
Okay.
zinc hydroxide.
Okay. Oh yeah. Okay. Got it. Yeah. So this is one of the problems where I have like 6 different ones, but still I might have a typo in just the strontium one. So let's double check this real quick. And I haven't done my rechecks to make sure I don't have typos in the key. So this was looking at strontium iodate.
Mm-hmm.
Yeah.
So that's going to be SR IO3 2.
2, correct.
This associates to SR2 plus 2 IO3 minus, both aqueous. We're doing this in water, so we start with 0, 0 plus x plus 2x, x, 2x. We get, what's the KSP value?
1.14 e to the negative
7 is equal to 4x cubed. We end up with our x value equal to?
I got 0.00305.
0.003.
Yeah.
3.05 times 10 to the minus 3. Grabbing a calculator, double check that. Do you know if you got this same number, Victoria?
I didn't hear what she said. I was still trying
This
to
number.
the
That's okay.
Part. No, I didn't. I got something different. I'm gonna see where I got that now.
Do you have your work by any chance?
I was literally just thinking that, and I think the notebook that I tracked my work in is the other notebook that I have
Gotcha.
at home. But I'm
No
gonna
worries.
compare that to this when I get home.
Okay. 3.05 times 10 to the minus 3. Great. Okay. So places where it could go wrong, and I would love to. I look at what answer you got as well, because I'm willing to bet it's a typo someplace. Because like this all makes sense. Yeah, this looks all familiar.
Yeah.
Right. So places where things can go wrong, the 4 versus the 2 is a big mistake people make, right? Because it's 2x squared, so it ends up being 4x squared. It's 2x quantity squared. That's a common mistake. And then third root versus square root, a couple of math mistakes there. But I get this value. Okay. And then you put that in, and that gets you part A, right? What'd you put for part B?
I multiplied it and now I got 0.0061 and I multiplied by 2 because it's 2
Yeah.
of those. But
I agree with
somehow I
you.
got 7 e to the negative 3, so I think I messed up on the calculator.
Oh.
Yeah.
Yeah, so we just,
remember
we
I
just
didn't know how to
doubled
plug it.
this.
Yes.
Yeah.
I was
And I
like,
get 6.11 times 10 to the minus 3.
yeah. And
which
you
is like,
multiply it because there's 2 of those.
Yeah.
So I don't know.
And you got
Yeah.
7 something.
Yeah, my calculator.
How? In any case, it happens.
Yeah.
It happens. Main thing I will recommend is you can resubmit answers on the quiz. As long as you're still within your time window, you can resubmit answers on the quiz. So one of the things I'd recommend doing is like go through, get your answers in, and if you're like, oh, I've still got 10 minutes, recheck some stuff. During, like, have your work laid out as clearly as possible, because then you can double check your work more easily. I can double check your work as well if you want to find out where you made a mistake.
I have a question on quizzes. Why is it not like LabPow where it tells us that we are correct? Like, I feel like seeing that we are correct would like stop overthinking in the quiz.
Well,
like, oh yeah, but also on a quiz you don't know if you're right.
Yeah, that's
Because
the whole.
like we all have like different numbers, so like I feel like knowing that it's like correct.
So the idea here is, and then part of the way that I try to prep you for this is the graded questions on the homeworks where you don't get to know if you're correct or not.
Yeah.
Right? So the quizzes are kind of built off those ideas of, if I were to make it so, like the problem is, I don't know if there's a way in LabPow to restrict the number of times you could try it.
Okay, yeah, that
And
would
if
make
I were,
sense.
and if I were going to tell you if you're correct or not right away, I'd only allow you one submission each time.
That would make sense.
But since you can retry things, you can be like, oh wait, no, I typed it wrong. Like, that's why I can't tell you right away if you're correct or not.
Is there a way we could submit like our work to the quiz so like if we do
Oh,
mess
yeah,
up
like partial
somewhere,
credit?
get partial credit?
Generally, no, but you can always talk to me, and like, if it's really something silly, like, I put, like, if you can show me work, this is more common on the exams where the points are worth more, lots of partial credits available. But on the quizzes, generally no. If it's something where it's like like several silly mistakes where it's like, look, I have it all written in my work correctly, but I didn't put this number in. Like, I have x, I have 2x, but then I have 7 times 10 to the minus 3 here, and I have no idea what I did in my calculator. I would try to give you partial credit for that. So yeah, the problem that I run into, not with all of you, of course, not with the people watching the video, of course, But I have had people come in with work that they did after they knew what the right answer was and be like, oh, here's my work. And like try to get partial credit back on something for work that they didn't actually do during the quiz. And there's enough inconsistencies in the numbers they inputted versus the work they're showing me that I'm like, well, can you explain to me how they did this? And they're like, well, this is my work. And I'm like, well, explain it to me. And like it becomes a really big headache. The safe way to do it is, and I've had students do this before where they're like, hey, I just made a mistake. I just submitted this, but I wanted to show you my work because I inputted the wrong number. And as long as the timestamp of like everything is really close to each other, where I'm like, you didn't have extra time to do this. I'm more willing to kind of take that into consideration. It's when I have students come up like 3 or 4 days later to like get credit because they're like, now that they know they got it wrong and they know like they can work with other people over a couple of days and they're like, here's my work. It's just like too late. So yeah, that happens sometimes, but generally the quizzes are a little bit harsh.
Okay.
So that's number 2. Victoria, I really want to know what you did wrong.
I do too. And now I'm sitting here and I'm so frustrated because I'm making all the mistakes I think maybe I made. Like I used 2 instead of 4. I messed up the Q root. I checked all those mistakes and this mysterious, like I understand this completely, which is why I've been like in tears because I understand this and I don't know what on earth happened. And I'm not, so I was like, what did I do to get this answer? And I literally have my notebook with all the steps just on my kitchen table, but it's like, that's why I'm frustrated because maybe the understanding creeped in after the quiz, but I sat through this quiz. It only took me 20 minutes and I thought I got them all right. So, and I wasn't rushed. I just felt like, wow, these calculations just don't take as, once
you practice them, they go pretty quick.
Yeah.
Now, the catches, like I'm looking at your numbers.
I can't even figure out where that number came from. But I purposely didn't look and I just purposely solved it through on my own and I'm like, that's what I would have put. And it's like, what on earth?
Yeah, the one that's interesting to me is your A to B, you did triple instead of double. So like the fact that you got something wrong in A is one thing, but your A to B is tripled instead of doubled.
Yeah.
Which is also strange. So there's there's 2 ways for me to kind of read this and understand it, right?
Yeah.
One is test anxiety, test stress, things like that. Time crunch, but you said you finished quick.
I finished quick feeling like I moved at a normal pace. So it was like I moved through it feeling like the understanding was just there. And I'm looking at like, why on earth would I have had a 3 instead of a 2? And then I'm looking at it like maybe I looked at IO3 and that's where I went with it. Or I don't know, but.
Oh, let me check one more thing.
It's helping me that right now, sitting right here, I'm fully understanding the concepts. Like that makes me feel better. I'm not super attached to this point, Like, because I know that the quarter will move on. It's just, and all the rest of them too. Like even this one. Look at.
I can help with this one. I know how to do that one.
Okay. So let's do this. Okay, let's go on to number 4.
I added the lone pairs, but then I remember in the homework you told me, well, not you. We discussed not having to include lone pairs. So I had included all the lone pairs, and then I went, oh, no, you don't need those lone pairs. They're implied, but with the negative. So I had included the lone pairs, and then I didn't because of that. Remember that one comment?
Yeah.
So I actually had all the lone pairs tip-tappitied in there. And then I was like, no, remember, so.
Well, that one, we'll have to look at that one together because I feel like you have that one correct and I feel like there's something strange going on there.
Okay.
So, particular, and I've got a particular in mind with something that you just said. So we'll look into that in just a moment.
Okay.
Because other than that's something that I thought would also be right. The only difference was on mine was that I had lone pairs.
The lone pairs, so the lone pairs can be included, but they don't need to be.
Yeah.
So we'll talk about that one in a moment. Here's what I want you to do. See what you can all do with number 4 before I do it on the board.
I haven't, well, I did the same thing on my quiz, because I feel like I'm right, but then I don't know why I'm not getting it right.
Right.
Okay.
Oh, and you've got your work here.
Yeah.
Do me a favor.
I
What's that?
got number 4 right.
You got
so
number
I
4
think
right.
also-
Right, but I want to see what they do with.
Yeah.
Let me take a look at your work real quick and
This
see
is
what
what
went
I
wrong.
did for that one.
But I
put negative
I
5 on
three
the
two
quiz
again,
instead
right?
of negative 4.
Why?
I don't know. And then my work that I tried doing right now was right there. That's my new work, but the other one was my previous.
So that's your new work. And then how do you switch between them?
Just click on
Oh,
this.
it's that one.
Yeah.
Okay. This is your old work.
Okay, so it's in 0.15
Because I don't know,
milliliter,
I feel comfortable with
sodium
the ice
iodate,
tables, but then
which means the concentration of iodate
I don't
to
know where
start
I'm
with
going
is
wrong.
0.15, right? Okay, that's what I'm doing.
So you got 7.644 times 10 minus 4.
yeah. And then on the thing I just put negative 5.
Sorry, I shouldn't laugh at that, but it's
No,
just
no,
like.
it's fine, because me too. I'm like, why did I?
So then
Because I
this
did
is
get
2x
7.6.
Remind me of your
0.15
last
plus
name.
2x,
Dominguez.
yeah.
Because if
But
you
in
check,
that
I put
moment, I would do the
7.6
x small
e to the negative
approximation.
5.
Yes,
But I got
this
both
is
for both
squared.
7.64 times 10 to the negative 4.
And that's the
I
right
forget
answer.
that a lot.
Yeah, and I
Yeah,
put negative 5.
Squared, so you still.
Just a
even-
typo.
just like the
I
X is small makes
Just
me
a
forget
typo.
sometimes to add
But I do
the
understand the
squared.
concept.
That's good.
Just square the 0.15.
Let's look at this. So I've got my
Oh, that's
KSP,
frustrating.
and then
It
I've
is,
got
because I was
X,
like, I
and then I've got
understand it, but why am I getting it wrong?
0.15.
So my work is right. It is negative 4 instead of.
Yeah.
I just did it.
Yeah.
So if I hadn't have
Okay.
squared that, then I did 4.01 times 10 to the negative 9
Mm-hmm.
divided by
So we're just gonna redo this because we've got the video going.
0.2.
So we
I
can-
figured out my mistake.
What was it?
I did the x is small approximation and forgot to add the exponent still.
Oh, yeah. So you didn't square it.
Yeah, so what I
Yeah.
ended up with is dividing by the initial concentration of iodate.
Not the initial concentration
But I
squared.
feel better now, because conceptually I
Yeah,
see
yeah.
yes.
Yeah.
Okay.
What was the initial iodate concentration?
0.15.
0.15?
For me, it was different, but.
Yeah,
Oh,
you got
yeah.
different numbers. Plus x plus 2x, x, approximately 0.15. You'll notice a lot of times when I'm solving this in the classroom, I still go through the trouble of writing KSP is equal to barium 2 plus times IO3 minus squared, and then I plug in all of my numbers. So I plug in the KSP for barium iodate
Mhm.
is,
Oh.
0.0225.
that's the KSP?
Oh, no, sorry.
the
That's
answer.
4.01 times 10 to the negative 9.
Sorry. I give you the one for this one.
Yeah.
Oh, gotcha. Yeah, is equal to x 0.15 squared, and then we can get to x is equal to, I can't do that in my head today, but it's something on the order of -7.
I don't do math in my head like you do math in your head.
I
Every time
got
you do that, like-
1.7 e to the negative 7.
1.78, yeah.
Every time you do the math in your head, my friends and I just like look at each other like, how
Yeah.
are you doing that?
Okay, so here's why I was like, I don't know, 0.1
Mhm.
instead of 0.15. 0.1 squared is 0.01. That's like just a factor of 10 difference, so that 987.
That makes sense.
So I knew it was like 10 to the
Yeah.
-7 something, and then I could have done, well, I know it has to get smaller because 0.15 is bigger than 0.1, so I knew it should get smaller as well. So I could have gotten it closer, but there's limits. It's already been a long day. Okay, so that's number 2. Problem 4 on quiz 1. We had a couple weird typos. forgetting our exponent on the iodate concentration, just putting in the wrong,
Because there was a cat.
not even the wrong sig figs, just the wrong exponent.
Yeah.
Best thing I can say is I try to make it so the quizzes have generous timing. I don't know if anyone has felt like time stressed on these. Right? Were you running at like the point of that is so you can do it. Like my recommendation is get one answer in for each thing, and then go back and be like, okay, well I've got time. Let me double check some work. Because I think the quiz this week you had 40 minutes, so if you finished it in 20, working at a steady pace, there's enough time to essentially redo all of the problems a second time and see if you get the same thing again.
I think that's helpful to know. I didn't know until you just mentioned you could resubmit answers.
Yeah.
At the end of it, I sort of had this feeling of, well, what's done is done kind of thing. I feel like
once you hit close page, like
It
once
is
you close
done.
the page, then it's done.
Yeah.
But on each problem, you can reevaluate each problem as you go,
Okay.
just like with the graded questions.
Yeah, and this is just old person to old person.
Yeah.
I've never done anything computerized like this.
Yeah.
Like quiz-wise, I'm used to a piece of paper and I'm sitting there and I can like kind of look through it again.
Yeah.
And when I submit it, it's handing it to you. And like,
Yeah.
so this is all really new to me. Typing
Yeah.
it all in is new. And
The number one thing I tell people, and it's funny because doing it on paper is the thing everyone should do. Like every time you have like quiz questions or anytime you do a quiz, I should be able to say like, oh, let me see what you did on the
Yeah.
quiz, and you should be able to hand me like all that paper and
Yeah.
like have me look through it
I'm
and
going to
figure
show
out
you
what's
that,
going.
and it's going to be exactly what happened. Is my exponent wasn't there, and like, cause I got the wrong answer by omitting the exponent.
Yeah.
And
Yeah.
so I'm like, oh, that's what happened. I went x is small, it's just 0.15, and then I forgot. Yes.
Yeah.
Yeah.
Okay, now that we got the quiz questions out of the way, should we go ahead and look at 1.2 and 2.2?
Yeah. And
Nothing from 2.1? Can we do 2.2 first?
Yes.
Okay.
I might be the only one that's on that. But they should be pretty quick questions.
Yeah. Okay.
The 6 I worked through and I'm like really sure I did it right, but it's wrong, and I was working through it with a friend and she also got like the same thought process.
Okay.
And then I like looked it up too to like see like, oh, did I make a mistake when I was writing it out or something? And online was also saying that I got it right. Not that online is trustworthy, but I was
Well,
confused.
I coded these problems, so it's also possible that I have mistakes in place. What is number 6?
Lactic acid, it says lactic acid is a weak monoprotic acid if the pH of an aqueous 0.1 molarity lactic acid solution is 2.43. What are the Ka and pKa of lactic acid?
Okay. And you looked up the real value.
I did it like by myself first, so
Okay.
what did I? Yeah, no, I didn't look it up until after when
Cool.
I was like
Now,
double checking to see if I'd written something wrong or
the
something.
thing is, sometimes in these problems I give like, usually I give specifics where I'm like, oh, someone did an experiment and determined the pH is this. It
Mhm.
might not match the literature value.
Yeah.
So let's go ahead and let's think about what's going on
looked it
here.
up after to
Yeah.
like see if I.
So we've got, and you can tell me if this is going the same way, so you tell me how to start the problem.
I first found the concentration of the hydrogen ions.
Okay, so you just did
Yeah, I did that first.
H3O plus is equal to 10 to the negative 2.43 is going to be like 0.000 something.
I got 3.72 times 10 to the negative 3.
Great.
And then I wrote out the reaction.
Do you write water first because you end up kind of ignoring it?
Yeah,
Okay.
just keeps it out of the way. And a lot of times you notice I like won't even write it. Eventually later in the quarter I'll be like, you all know water's there. Sometimes I'll write it over the arrows to be like it's lactic acid in water.
And why are you writing H-lac instead of
Laziness.
Okay.
Right. So not laziness so much, right? I could write out the chemical formula for lactic acid, but the reason I like doing this is it really accentuates the fact that it's a proton and a lactate anion. And whenever I do this, what's that?
It doesn't write it like, it does like C3H6O3.
Yeah. So whenever I do this, I like to also have a definition. So this is C3H6O3. Right, so I'm just using a shortcut. This makes it so all weak acids kind of look the same.
Like,
So
I
then-
mean, the lactic acid is H6O3. So I guess
Wait.
yeah, that would be the lactate.
Yeah. Let me double check that real quick.
Wait a second. Lactic acid
Is the
is C3H6.
O3, and then so that's just lactate, which is when it's
Oh,
not an acid.
Yeah. So I did
Yeah.
that right. Okay, so
Yeah.
on the right-hand side of the equation, we just ditched a hydrogen,
Uh-huh.
formed a hydronium.
Now, we've got, it's talking about pH. Do we know its initial? Change, equilibrium. What's the question ask? It asks for
It's
the,
asking for Ka and pKa of
Okay.
lactic acid.
we got 0.1. Lactic acid, lactate at the beginning should be 0. Hydronium at the beginning
Zero.
should be 0. I'm gonna have minus x plus x plus x. I'm gonna have 0.1 minus O. I think I know where this is gonna go wrong. Now, catch here is, we know x, so we can plug x in.
Ooh. Yeah. Wait, hold on. I forgot. Yeah, I did the x's small and didn't.
Yeah, you don't need to do the x is small approximation.
That's what I did.
Yeah, so we don't need the x is small approximation in this case. So we will get two different Ka values. Ka is going to be x squared over 0.1 minus x. Now, you could argue, well, 3.72 times 10 to the minus 3, x is small approximation should work. So if I do 3.72 times 10 to the minus 3 squared divided by 0.1, I get an answer of 1.38 times 10 to the minus 4.
Yeah, that's what I got, and it says it's not right. So it must have mattered.
Versus the one that I was expecting. So let's see how different this is.
Oh, it's like 4 orders of magnitude different. It's like
What?
Or maybe I'm doing it wrong because honestly, I don't normally use this calculator, and it's being annoying. But
my guess is you forgot a parenthesis someplace if
Oh,
it's
I
4
put
orders
it-
of magnitude of difference.
I put a lot of parentheses.
So wait, is 1.44 times 10 to the negative 4th right?
Yeah. Now, normally, so that's not a huge difference between it shouldn't be 4 orders of magnitude.
I don't like this calculator. I can't find my charger for my other one, and I've had to order a new one. But
New
while I'm
charger.
waiting for it to order, I have to use this one, and I don't like this one.
Sorry.
It's okay. It's
And
not.
so to do the pKa, remind me, this, hang on, I've got it. So it's the negative log of Ka.
Yep.
Okay.
So we take that, and it's going to be like 3.7,
I'm
oh,
doing something
3.5. No,
3.8.
3.8. Yeah, sorry, rounding wrong.
I'm doing something wrong.
Let me see.
Because it's my
Calculator.
calculator. It's my calculator being weird. But because now I know what I did wrong. I just
1.38 times 10 to the minus 9. 3.72. Oh, well, you put minus 5 instead of minus 3.
why did I have a 5? That would do it.
So that's why it's going wrong now. It's just a different typo in your calculator.
Okay.
So let's put it at
Is that a
minus
4?
3.
Yeah.
So you should get
Can I
1.3
please
times
zoom
10
out?
minus 5, not 1.38 times 10 minus 9.
Can we explain how we got this? So
Why did I
Ka equals
write
the concentration of X. Oh, how you got this expression? Like where that expression came from?
No, the actual number, the 1.
What we did is, we already know the X value because at the very beginning of the problem, it gave us the concentration of hydronium, and hydronium is X. So we input 3.72 times 10 to the negative 3 as the X value.
Oh, and they used.
And we're not assuming X is small here, we're actually inputting that X value because it's given to us. And so to get that number,
Mhm.
we put the 3.72
And both.
into X as
Oh,
X.
okay,
Yeah.
thank you.
So let me see here. I'm going to try to do something real quick. So yeah, so I have a much smaller percent range allowed in this problem because normally I have like a 5% error range and like these two are within 5%. I've got it down to a 2% error range because I didn't want people to use the X small approximation, but I'm going to add something for future students. Excuse me, that checks if the X small approximation is used or not. Oh no, there's my square. Okay. For a second I thought in my key I forgot the
Oh, okay, I got it.
Yeah.
Thank you.
Yeah. I can already, like, as we're going through these, as soon as they're set up, it's like I can feel myself able to flow through them. But looking at the question, just looking at how it's worded, I don't think I would have been able to set this up. Like, I can see that, like, starting all of these is where,
What helps me a lot with the acid-base ones is writing out a reaction first. I don't know, that's been helping me with that, because I've just been kind of doing things and then been validated by it being correct, but.
Okay, let's see if I did this
Oh,
right.
there was such a small difference in the things. Okay.
can I see what you did for 4? It's conceptual, so it's not much math, but, or could you explain
Okay.
those?
Yeah, so I wrote down in the lecture, I got it from the lecture, that, that pKa plus pKb is equal to pKw. And then I know that, where did I write this? I know that Kw is up here. That Kw is 1 times 10 to the negative 14. So pKw would just be the negative log of 1 times 10 to the negative 14, which is 14. And then that's what pKa plus pKb is equal to.
Just 14.
Yeah.
Okay.
Speaking of 14, should we do number 14?
Yes, please.
Okay. Ready for this to get erased?
Yes, yes, yes.
Also, if someone wants to try this, if you refresh your page and try putting in our X small approximation, does a new hint come up? I tried changing the coding a little bit so it wouldn't frustrate people as much in the future. So, okay, while you do that, I'll go ahead and set up number 14 on the board.
Yes, it does.
Cool, okay. Now let's pause a little bit. Looking at number 14. What is number 14?
It's a Molar solubility question.
Okay.
Practices with that because a lot of them hadn't been, like we hadn't been doing ice tables, but then this one we are. It says, what is the concentration of magnesium ions in a solution that already has a pH of 12.77?
Ah.
Yeah. And then it just says like use KSP values and stuff. And
What use KSP values does it say?
it just says use KSP values from the equation sheet.
Okay.
And then it
What
also says
KSP values would you use?
for like magnesium hydroxide.
Yeah. Why magnesium hydroxide?
Because like
It's in water with a pH that is
12
high. It's a basic pH. So there's a couple important things that come out of this, right? Conceptualization, right? It's weird to look at this and be like, wait, what am I supposed to do with this? There's like so little information given.
That's right.
So there is a trick that I do that I tell other students. I don't think I've done it in 129 this quarter, but essentially what I write down is I look for explicit information. I look for what result I'm trying to get to. And then every question, this isn't just in chemistry, but every question in like every college class has some implied information in between the explicit information they give you and the result they're trying to get. In history class, they'll be like, what's the importance of the War of 1812? So you're looking for something important, you know it's the War of 1812. They assume you know something important about the War of 1812. You know what I know about the War of 1812?
It was in 1812.
That's about it. Right? That's explicit information. That's explicit information that's there. It's not the implied information, right? And additionally, context matters because what's important about it, depending on who the instructor is, what kind of lesson plans they went through, different people can find different important things in these historical contexts. Chemistry, in some ways, is a little bit nicer because, not nice, it's just a little different because there's usually, there's more rigidity towards what we're doing. So we say, okay, what's the explicit information that we have? We know that we have a pH equal to 12.77. The result we want is we want to get our magnesium 2+ concentration. This problem has a lot of implied information. There are several things we have to do in order to get between these two things.
Because I like started doing stuff and then got stuck. I was like, well, that doesn't feel
So
right.
we know pH. So
Can I-
I start to map things. Yeah.
Sorry to interrupt you. Can I ask you a quick question?
Sure.
If we were sitting here staring at this and not having an idea where to start, it's 11 o'clock at night, you're not in office hour, we're not in,
Yeah.
like, where do you recommend, like, we go when we've got this limited amount of information? Like, do you recommend we go to our brain banks of things that you've taught us in class, or is there a way that we can, like, is there a place that we can look up some way to start a problem like this? Because it's starting it. It's not that I can't.
Yeah.
You know?
So this is why I'm trying to show you like how I start things. Old office hour videos. I have office hour videos from like 2019 that are posted for Chem 129.
Okay.
So those old ones, like some of these problems, like the problems have changed. I do things a little bit differently.
Mm-hmm.
It's been a couple of years. But some of that stuff might be useful. Some of the textbook problems, there are problems in the textbook that kind of set that up. The additional problems the additional problems workbook has things solved for Chem 127 and 128, but not things for 129.
Mm-hmm.
So not there.
Well,
And then just kind of like the thing that I've started bringing up today, which I don't know if this is the right way to do it, but like the environmental construct, the social constructs that kind of give us hints,
mm-hmm.
right? Like the fact that we talked about KW for 10 minutes and then the answer to the next question that I asked was, it's the KW.
Mm-hmm.
But everyone was like, we have no idea. Like no one in the class knew what I was trying to do. I was just like, how do these relate to each other? And everyone was like, no idea. Right? And it's like, what did we spend the last 10 minutes talking about? I'm like, acids and bases. What specifically? It's KW. KW is what related them. So we go to like, okay, well, what's the context? What do you know about pH?
That's a basic pH.
Okay, so this is basic. That's one thing. Low pH is basic.
pH tells us some information about the concentration of protons or the concentration of hydroxide. Not
pH tells us about H3O+.
Okay.
How do we get from H3O+ idea to OH? What else? You also mentioned it also gets us to OH- concentration, right? We know from class today that those two things are related to each other.
Mm-hmm.
Then that's going to be through the KW, right? This is a low pH, so my H3O+ concentration should be really small. My OH- concentration should be kind of big. And now I say, okay, well, if I've got hydroxide in solution, I've got H3O+ in solution, I've got OH- in solution, I've got Mg2+ in solution. which things might interact with each other?
Magnesium hydroxide.
Magnesiums and hydroxides. The hydroxides and the hydronium could interact with each other, but we've already got a stable pH, so that's already happened.
Mm-hmm.
The magnesium ions and the hydronium ions are both positively charged, they push away from each other. The magnesium ions and the hydroxide ions might interact with each other. So then we go ahead and we say, okay, well, what is the KSP for magnesium hydroxide? Do they interact with each other well or not?
It's 5.61 times 10 to the negative 12.
Whoa.
So conceptually, really quickly, tell me one more time, how this KSP tells me if they're going to interact well or not.
Ooh, you tell me.
Okay.
What's KSP tell us?
If they're
KSP tells me if those want to stay together or split up.
Right.
They are either in a good relationship or a bad relationship.
Yeah.
And if that number is really small, it means that they are done with each other and they want to split up if it's small.
Ooh,
Did
you
I
got
get that
backwards.
wrong? See, I keep getting this conceptually wrong. If the number is very, very, very small, they want to stick together.
Well, and we have to be careful about this, right? Because big number versus small number for what reaction? Right? This, when we're talking about KSP, we're looking specifically at magnesium hydroxide splitting up.
Yes, yeah, so I got that in my head. Magnesium and hydroxide are more likely to split apart if the KSP is larger.
Yeah. So large equilibrium constant tells us towards products. Small equilibrium constant tells us more towards reactants.
Okay, and if it's a small KSP, it means it will precipitate first.
Small KSP means more solids.
Okay, and so if we were looking at that other problem set, talking about what's going to precipitate first and what's going to precipitate second, if that had an extremely small KSP, it would precipitate first.
Yeah.
Okay.
Compared to the others.
Because it wants to be a solid.
Yeah.
Okay.
Right.
Okay.
So yeah, and for me, like, to make sure I don't mess this up, I often have to write down the chemical reaction and be like, okay, solids, because small value, remember, all of our equilibrium constants are products of reactants. This small number means small amount of products, which means mostly solids. So from this, I'm like, okay, I know magnesium and hydroxide are going to react with each other. I can calculate my hydroxide concentration. I've got a KSP value. So I'm just going to do, now I can solve, like, after all of that, now I can solve the problem. I'm going to have my magnesium concentration going to be equal to my KSP divided by my hydroxide concentration squared.
I was writing it out, like, weird, in a way that was confusing me.
And notice, there are so many steps to get to this. And it's really hard if you're like, well, all the problems I've had before, I've had so much information, what do I do now? It's like, well, slow down. What bits do you know? We know that this is all done in some context of this chemistry class where we're learning about this particular topic now. This would be a really weird question if you were in a soil science class and they were just like, what's the concentration of magnesium ions at a high pH? It's just kind of like, well, what soil? Like, you'd want to have so many questions about, like, are we in a desert? Are we on a coast? Like, where's the soil coming from? Like, your context for how you think about magnesium concentration is, like, completely different if you're in a different class. In this class, we go, okay, the only number we're given is the pH. I have to think, what do I know about pH? And you all said pH can get us to H3O+, H3O+ can get us to OH-. We know it's low pH, so it's basic, which means there's got to be a significant amount of OH-. Then we can do the next step of thinking, which is, if I know chemical compounds are present, what reactions could occur? And that's where we start getting the KSP stuff. And I just realized I've been ignoring you this entire time. I'm so sorry. I get so caught up with 129. I saw you there. I knew you're from 353, and I, like, didn't stop. You gotta stop me. Okay.
So
I'm gonna pause this and answer another question.
But how do we